In this lecture, we will discuss about Coset. So we write down the definition of Coset. So we understand about the group, subgroups. Then the further we will discuss about the Coset. So we write down the definition of Coset. So let H be any subgroup of G. Subgroup of G. So then for any number, we consider A which belongs to G. The set HA is equal to HA such that H belongs to H is called right coset. So on the basis of this variable A is called right coset. Right coset of H in G. Because H is the subgroup of G, the GB also is the group. So we write down this as, when we write down the AH, so AH is equal to A into H such that H belongs to H. So this is called left coset of H. Is called left coset. Left coset of H in G. Now we take some examples related to that. So we write down a let G be any group for understanding the definition of coset. So G contain the element 1 minus 1 iota and minus iota. So G follow the property of group. So then and H be any subgroup of G. H be any subgroup of G. So H we consider as 1 and minus 1. We take two elements. So we H is subset of G, or H is itself a group, because H is also satisfy all the properties of group. So H is a subgroup of G. Now when we are going to write the right coset or left coset of H, so the right coset of H in G. So for value, we take the A is equal to iota. So we can take any value from G. So that means we can take I A equal to 1, minus 1, iota and minus I. Suppose we are considering the value A equal to iota. So that means in a definition of right coset, so you can write down as H into iota. So in place of A, we put iota. So this equal to our H is H belongs to H. So H having 1 and minus 1, two elements. So we write down as 1 into iota. We do the product with iota because we have seen that means H into A. So into, and second element is minus 1. So we write down minus 1 into iota. So this gives us iota and minus iota. So this gives us iota and minus iota. So this is our right coset. Right coset of H and G. So now we are calculating the left coset of H in G. So for left coset for same element, that means A equal to I. So we write down as I into H is equal to, so iota into 1 comma iota into second element is minus 1. So this also gives us iota and minus iota. So here we can see that the right coset is equal to left coset. So that means here we can write down a right coset is equal to left coset for this particular example. Now We have a one important theorem. That theorem says that if left coset is equal to right coset equal to h. Okay, when we are taking the element of left coset and right coset, this equal to also h. So now we will prove this theorem. So the statement of the theorem is, or you can understand for this one. So that means we can consider this example. We can extend this example. So when we extend this example by using the value of a equal to 1, using the value of a equal to 1. So generator, we can write down h into 1. H into 1 gives us 1 into 1 comma minus 1 into 1. So this gives us 1 comma minus 1. Similarly for 1 into h, that means right coset and left coset. Left coset 1 into 1 and comma 1 into minus 1. So this gives us also 1 comma minus 1. So here we see that the value of left coset on right coset, so h1 is equal to 1 into h is equal to h. So we see that that means 1 minus 1 element of right coset and same as left coset or same element of the h. So now we will prove one theorem related to that, left coset equal to right coset equal to h. So the statement of the theorem is, so we have very important theorem related to coset. So let H be any subgroup of G. So let H be any subgroup of G. So we are using G. The G itself a group. This is understood. We do not write every time the G be any group, H be any subgroup of G. So when we are writing H be any subgroup of G, G means G itself a group. And H belongs to H. Small h belongs to H. So then H is equal to H equal to H. So this is the very important theorem. So right coset equal to left coset equal to H. So now we are proving this theorem. So for proving this theorem, so we assume that, let us assume that H be a subgroup of G, H be a subgroup of G, and small h belongs to H. So then H dash into H belongs to HH, means right coset. So here, this H dash belongs to H. So we can write down as where H dash belongs to H. Because this element H, that means right coset element. So we write down the, as per the definition. So the definition we have HA equal to HA. So this A belongs to G, so means also belongs to H. So here H belongs to H, so we write down as H dash H belongs to HH. Now, by using the closure property, by using the closure property, we have two elements. One element is H dash. We have two elements. One element is H dash. H dash belongs to H. Second element H, which is also belongs to H. So this implies that H dash into H belongs to H. So we have taken the element H dash H belongs to right coset of H, or this H dash H belongs to H. So from these two statements, so that means this statement and this statement, we can write down as HH, all the element of HH in H, so HH is subset of H. So this is our equation number 1. So those element who belongs to HH also belongs to H. So HH is the subset of H. Now we move to the further. So that means again let H dash belongs to H. So H dash belongs to H. So then we can write down this as H dash into H inverse. H dash into H inverse into H. So H dash into H. So this can be written as, that means H inverse into H, you can write down as E. So you can take as, so this H dash into E also belongs to H. So we can write down this as, this implies that H dash into H inverse or H, which belongs to HH, means right coset. This belongs to right coset because H belongs to H. H is a subgroup of G, so its inverse also exists. This inverse also exists as the H inverse also belongs to H. So H inverse also belongs to H. So that means when we can take two elements, so H dash into H inverse is also belongs to H, because we know the property, if A belongs to H, B belongs to H, which implies that A into B inverse also belongs to H. So by using this property also, we can use this property. So we write down as one element we can take as H. Okay, so H dash belongs to H. So when H inverse also exists, so AB inverse also belongs to H. So we can see that when we take this element H dash, which is belongs to H, the same element H dash also belongs to HH by using the definition of right to set. So this can be written as uh, H is subset of HH. H is subset of HH. So this is our equation number two. So this is our equation number two. So from one and two, we can write down as H is equal to H. But HH is subset of H. Here H is subset of HS. So HH equal to H. So this we have proved for right coset. Similarly, so we write down here as similarly, we can prove for left coset, means HH equal to H, and hence we write down as right coset is equal to left coset is equal to H. So this is the theorem, very important theorem. Now we have a one example already we have given. Another example you can take as, if G is equal to 1 minus 1 iota and minus iota, and H be the subgroup of G having element 1 and minus 1, and when we consider H is equal to minus 1. So we consider as H, H is equal to minus 1, which also belongs to H. So this minus 1 is also belongs to H. So when we want to write the right coset H of minus 1, so this H of minus 1 is equal to 1 into minus 1, comma, minus 1 into minus 1. So this gives us minus 1 into 1, sorry, minus 1 into 1. So this gives us minus 1 into 1. So this is also the H. So we can write down right coset of minus 1 is equal to H. So similarly, you can solve for the left coset. Now we move to the next theorem. So next theorem is, let H be any subgroup of G. Let H be any subgroup of G. So there is one-to-one correspondence between any two right cosets of H in G. So we can obtain the one-to-one mapping between two right coset of H in G. So how to prove this theorem? So for proving this theorem, so let A and B be two element of G. So let A, B be the element of G, and let H A, H B. Okay, both elements belongs to G by the definition of right cosets. So H A and H B be any right cosets of H in G. So when we are going to define, so that means we are defining, suppose this is the right coset of A, this is the right coset of B. So there is the mapping, or that mapping is one-to-one mapping. Each element of set A related to the unique element of set B. So that means we are just writing the one-to-one mapping. So this element related to this element, this, okay. So one-to-one mapping. So we define a function f such that HA to HB, right coset of A to right coset of B, by setting function we are setting in this way: h of A is equal to HB, right coset element of A is equal to right coset element of B for every H belongs to H. So we know that when we are defining the mapping means if this is the function X, this is the Y. So that means a mapping S from X to Y. So we define as function of X tends to Y. So we can say that function of X equal to Y. So that means this is the domain. Here is this is domain. This is codomain, and the element which is related to the set X is called a range, and range is always subset of codomain. So range is always subset of Y. So here we also define that HA be the element of this HA, right coset of A, and HB be the element of this right coset of B. So H belongs to H. Now, so it is necessary. So for one-one mapping, one-to-one correspondence, that means a function of H1A. So we assuming that the H1A which is equal to function of H2A. Function of H1A is equal to function of H2A for one-to-one mapping. So we take two elements. So the f of H1A is equal to f of H2A. For every, we have consider as H1 and H2. These two elements are belongs to H. Okay, so we know that when we proving one-to-one function, one-one mapping. So how to prove one-one mapping? So we take two element of X. So that means we denoted as f of X1 is equal to f of X2. Now we prove that X1 is equal to X2. So similarly, okay, so these x1 and x2 we take element from X. So similarly, here we have also considered the element of right coset of A. So H1A into H2A we take the element of this first domain function. So this HA, so H1A is equal to f of H2A. So you remember this thing. So we are parallelly uh, understand the concept of mapping and one function. So we will prove that x1 is equal to x2. So now h1 h2 belongs to H. So this f of h1a, Here when we replace in this function, in this we replace h to h1. So f of h1 is equal to h1b. So this gives us h1 into b is equal to now h2a. So h replaced by h2 in this function. So this gives us h2 into b. So h1a, h1b equal to h2b. Now b be the element, a or b be the element of group G. Group G have satisfy all the properties. That means closure, associative, identity, and inverse. So it means that the inverse of A and B also exist. Yes. So A or B belongs to G. So then inverse also exist. Inverse also exist. Yes. So inverse also exists. So that means B inverse also belongs to G and A inverse also belongs to G. Okay. So now we take as so H1B into B inverse. This equal to H2B into B inverse. H2B into B inverse. So B into B inverse. This gives us HE, H2E. So by using the definition of identity, so H1 is equal to H2. So H1 equal to H2, we have proved that X1 equal to X2. So H1 equal to H2. Now, this we can write down as H1A is equal to H2A. We can write down as H1A is equal to H2A. That we write coset of A. So here we can say that function is 1, 1. So function is 1, 1. So when function is 1, 1, so now taking right coset of A. So now we shall prove that function is onto. So we shall prove that function f is onto. For onto function, we take the element of y and prove the image, pre-image of element in x. So that means we consider as y belongs to y. So then the pre-image of y is x belongs to x. So prove that x belongs to, then prove x belongs to x. So that means for onto function. So that means we consider the function of hb. Okay, so here we define already. So this is hb. So that means we consider as hb belongs to right coset of b. So for proving onto, so let hb belongs to the right coset of b. So HB belongs to right coset of B. So this implies that we can write down as H belongs to H, obviously. So H belongs to H. So this can be written as H belongs to the HA. HA belongs to HA by using the definition of right coset of A, because we have already defined H of A. H of A is equal to HA such that H belongs to H. Such that H belongs to H. So we can use this definition. So when H belongs to H, so we can write down HA belongs to. So here we can write down HA belongs to HA on the basis of this H. Okay. So HA belongs to right coset of A. So we see that this HA, this HA is the function of X. So this is the member of first function. That means HA set, right coset of A set. So that means the uh, pre-image of HB in HA. That means, so hence we can write down as function of HA having the image at HB. So we can say that function is onto function. Function is onto. So when function is 1, 1 and function is onto, so that means the function that also exists the inverse. So you can write down the order of right coset of A is equal to order of right coset of B is equal to order of H. So this can be. So first we uh, prove the function is 1, 1 or on 2. So the 1, 1 or on 2, the correspondence between them. So then we can write down the order of right coset of A equal to order of left right coset of B equal to order of H. Now, We will prove one more theorem related to that. So related to right cosets or left coset. So one more theorem. The theorem statement is that prove that the right cosets prove that two right cosets prove that two right cosets are either disjoint right cosets are either disjoint or identical, either disjoint or identical. Disjoint, what is the definition of disjoint? Disjoint, suppose uh, x1 and x2 belongs to set x. So x1 intersection x2 is equal to 5. So they are said to be disjoint. That means there is no common element between them. Okay. So for proving this theorem, so we consider as let HA, right coset of A, and HB, right coset of B, be two right cosets, be any two right cosets of H in G. So we consider as if possible right coset of A intersection right coset of B is equal to 5. So this equal to 5. So we are finished. So that means our work is completed. Now, but if H right coset of A intersection right coset of B is not equal to 5, so then in such cases, so then we can say that element C, which belongs to right coset of A intersection right coset of B. So how to prove this? That means we can take by using the Venn diagram. So Venn diagram says that this is HA and this is HB and CB an event which is common common between these two. So now we can write down this as C belongs to right coset of A and C also belongs to right coset of B. So we can assume that if C is equal to H1A, C equal to H1A and C also consider as H2B, H2B. So these H1 and H2, so we consider as these H1 and H2 both are the member of H. So H1A, so first H1 belongs to this H and second H2 that belongs to this H. So that means, so when we consider as C equal to H1A and C equal to H2B or H1, H2 belongs to B. So we can write down as H1A is equal to H2B. So H1A is equal to H2B. So this implies that that means when H1, H2 belongs to S, its inverse also exists. So we pre-multiply by H1 inverse. So pre-multiply by H1 inverse both side. So this gives us H2B and here H1 inverse into H1 gives us A. So this gives us H1 inverse into H2 into B. So this is our equation number 1. Now we write down HA. HA equal to H into H1 inverse into H2 into B. So HA. So in above equation, so we take as HA. HA is equal to H into H1 inverse into H2 into B. So this can be written as H into H1 inverse into H2 or into B. So you can see that we are taking that H1 inverse into H2. This H1 inverse into H2 we take as another variable H3. Another variable H3. So this H3, so we can write down as H3. H3 belongs to H because these two are belongs to H. Suppose we consider a equal to 1, b equal to 2. जब when we do the a into b, so this gives us 1 into 2 equal to 2. So 2 belongs to h. जब these two belongs to h, this also belongs to h. So h, when we do the product of two numbers, which can consider as h3 also belongs to h. So also belongs to h. So this can be written as h into h3, h into h3 into b. So h into h3 into b. So we have one theorem related to the right coset of h equal to left coset of h equal to h. So right coset of h equal to h. So this h into h3, this h into h3 we can written as h into b. So here we can get the h equal to hb. So h equal to a right coset of a is equal to right coset of b. So therefore two right cosets are identical. So we can write down as therefore two right cosets, two right cosets are identical. Two right cosets are identical if they are not disjoint. They are not disjoint. Means they have same element. Either HA intersection HB is not equal to phi. So we can write down a HA equal to HB. So this is the next theorem. Hope you understand.